Okay, so we have solved this system of equations using ease. That was almost effortless, I guess. We solved it using matrix decomposition. That took a little bit more effort, and it required that you have, some kind of matrix decomposition capability software, something that can, decompose large matrices. There's one third way that's kind of interesting, and that's Gauss-Seidel iteration, right? And that actually just solves explicit assignment type equations, which computers are really good at, right? So if you have a program like C or MATLAB or C or Fortran or something that's compiled, it's really good at flying through solving assignments one after another. So that may be a place where you want to use Gauss-Seidel iteration. If you want to use Gauss-Seidel iteration, then all you do is you take the equations we've already been solving. So this is 1, 2, 3. This is the equation for node 1. This is the equation for all of my internal nodes, and this is the equation for node n, right? So we've solved this system of equations twice now. We're going to solve it one more time. And the way that we solve it this time is you actually just take each of these equations and you solve it for the node that generated this equation, right? So this is an energy balance on node 1. I'll just solve this for T1. So everything that isn't T1 I put over here. This is an explicit equation for T1. Now it's written in terms of other temperatures I don't know. I realize that, right? But this is definitely an explicit equation for T1. This was generated by doing an energy balance on node I. So I'm going to solve this equation for Ti. That's what I've done here, right? This is an expression for Ti. It's written in terms of Ti minus 1 and Ti plus 1. Again, nodes that I don't know the temperatures of, but this is an expression for Ti. And this is finally one for Tn, right here. So this is the engine that drives the Gauss-Seidel iteration forward. And all the Gauss-Seidel iteration technique does is it starts with a set of guess temperatures for every node, right? So if you have a good set of guesses, that's great, but you need some place to start, right? So for my current lead, let's look at this current lead. This end is at 300, this end is at 40. I might decide that my set of guess temperatures is every temperature is the average of 340. Or better yet, maybe I decide that the temperatures are linearly varying from 300 down to 40, right? It's not the right set of temperatures, but it's a place to start, right? Those are my guess temperatures. So that's where I start. And then I use this set of equations. Once I have a set of guess temperatures, I just cycle through these equations and calculate a new value for the temperature at every node, right? So if I'm going to start with a set of guess temperatures, then the next thing I'll do is I'll come to this temperature, this equation here, and say, well, based on my guess temperatures, what is T1, right? So I'll solve this for T1, and then I'll come to this one and say, based on my most recent set of guess temperatures, which now has this T1, what is T2? And then what is T3 and T4 all the way up to n minus 1, and then finally what is Tn, right? So I've basically just recalculated all of my temperatures based on the most recent set of temperatures that I had available to me, right? And then I'll look at the new temperatures and I'll compare them to the old temperatures, right? So I'm looking at an error between subsequent iterations, and if that error is small enough, then I'm going to decide that I've converged. If it's not, then I use my new set of temperatures and just repeat, right? So this is an iteration. It's going to take some number of cycles to finally get to a converged answer. And what you call converged is a little bit up to you, right? So what's the maximum error you're going to allow between two cycles? But again, the nice thing about it is I'm never solving anything more than one equation at a time, right? Which computers are super good at. All right, so what that looks like in MATLAB is this. So here's all my inputs. This is the same thing. I set up all my nodes. I've decided to set up an initial guess for the iteration that every single temperature is at 300 Kelvin, which is a really bad initial guess, right? I know that there's probably better ways to do this, right? And then I'm going to say, all right, so I'm going to now calculate a new set of temperatures, right? And my new set of temperatures starts with the most recent set of temperatures, right? So the most recent set of temperatures at this point is T old. I'm going to do this inside of a while loop, right? So while the error between iterations is less than my tolerance, which I've decided is 1 millikelvin, I will keep iterating. And then all I do is go through that set of equations, right? So this equation, these n-2 equations, and this equation are hopefully exactly equal to these equations that I derived here, right? So you'll notice one thing is that I'm always using the most recent value of the temperatures over here on the right side, right? And then once I'm done, I've calculated all my new temperatures. What's the maximum difference between my original old set of temperatures and my calculated new set of temperatures? And here I'm saying, tell me what the maximum difference is, the maximum absolute change is, right? And if that maximum absolute change is greater than 0.001, then I'm going to go through this loop again and again. Eventually, it should go down to my convergence. And the last thing I got to do, which is very important actually, is before I do this again, I have to store what I have now as my T old, so that when I do this again, I have something to compare to. And because I did not terminate this statement right here with a semicolon, I ought to be able to see in the command window the iteration go down. So let's just run this. If I run this, what you should see are errors, and eventually the error goes down to 0. Again, it's a pretty fast way of doing it. If I look at the plot, where's my plot? It's the same, right? To within 0.001 Kelvin, it's the same as the other way. So that's just one more way of doing this. Which is better really depends on the problem. All right, so before we leave off of numerical techniques, I think it's important to come back and think about how we make these a little more powerful, right? At this point, I solved this problem 3 different ways, I guess one way, but using 3 different equation solving techniques. But it's a solution I could have gotten analytically, right? There's nothing about this that would have precluded an analytical solution. So if I want to make this into a problem that would have been really hard to solve analytically, I got to do something like, rather than have constant electrical resistivity and thermal conductivity, I would let them vary with temperature in some way, right? And how they vary with temperature is completely arbitrary, right? I mean, I could go to a function and have that function maybe interpolate a bunch of data, or it could be a very complicated equation. I am, for the sake of illustrating what I'm talking about here, going to use a very simple equation, which is I'm just going to let this K vary linearly, so it increases with T according to this equation, and the electrical resistivity also increases with T according to this equation, right? Nothing physical about this. It's just illustrating the idea that if I want to, I can put in temperature dependence of the properties, right? And again, this is exactly why I would have a numerical solution, is so that I can deal with these kind of complexities that I could not deal with an analytical solution. Okay, so how do I do this, right? How do I take the temperature dependence of these properties and fold them into this set of equations that I have right here? You can see that K and rho E, every place they appear in these equations, they're no longer constants, right? They're no longer a value that is just never changing. Every place I have a K and a rho E, they're actually some kind of a function. I have to evaluate that function at a given temperature in order to proceed, right? So the first question to ask is, what's the temperature I should be using to evaluate thermal conductivity and electrical resistivity in each of these equations? And the obvious answer, which is actually wrong, is that, well, this is the equation for node 1. Probably I should evaluate the conductivity at the temperature of node 1 and the electrical resistivity also at the temperature of node 1. This is the equation for node I. I should use the temperature of node I to evaluate the properties. And this is the equation for node N. I should use the temperature at node N to evaluate these properties, right? And that would be fine for the electrical resistivity. It's not going to be fine for the thermal conductivity. And to see why, we have to remember where these equations come from, right? So over here, this first equation, this equation for node 1, it comes from an energy balance on node 1, right? So, Q dot top, Q dot bottom, and G dot, Q dot top, Q dot bottom, and G dot. This equation right here that involves this thermal conductivity, that's the equation for Q dot bottom, right? This is the equation for the energy crossing this boundary being driven by node 2 minus node 1, right? T2 minus T1. So it's this equation right here. So if I go down one node, so from instead of node 1, now I go down to node 2, we can do an energy balance on node 2, right? This is one of these equations. This is the equation where I equal 2, right? So Q dot top plus Q dot bottom equals G dot. One of these terms is Q dot top, right? It's the energy crossing this boundary but going in the other direction, right? So it would be K times AC times T1 minus T2. So the point that I'm trying to make here is that, let me see if I can get my pen, is that this equation here is the energy transfer across this boundary as I'm doing an energy balance on node 1 looking down, right? This equation here is the energy transfer across the same boundary, but now I'm doing an energy balance on node 2 looking up, right? And those two energy transfers, this guy and this guy, well, they better be exactly the same. I mean, they might have a different sign, but they better have exactly the same magnitude because they're the same energy transfer, right? And if that's not the case, then at every single boundary in my computational domain, I'm going to be destroying or generating a little bit of energy, and my numerical solution isn't going to work. So if you think about what that means over here, if I just use the temperature of node 1 when I'm dealing with node 1, and I just use the temperature of node 2 here when I'm dealing with node 2, this guy and this guy, they don't have to be the same, and that's just not going to work. So what I need to make sure that happens is that the thermal resistance that I'm using here when I'm looking down on this boundary and the thermal resistance that I'm using here when I'm looking up on this boundary better be the same. And the way you make sure that's the case is you use the properties, you use the characteristics evaluated right at the boundary, right? So if my area were changing, I would be using the cross-sectional area right at this boundary. In this case, my conductivity is changing, so I better be using the conductivity evaluated right at the boundary. So what that means is I don't use the conductivity evaluated at T1 or at T2. Instead, I use the conductivity evaluated at the average of T1 and T2. Or also, alternatively, I could use the conductivity at T1 plus the conductivity at T2 divided by 2, right? But somehow, I better get the same answer no matter which of these two energy balances I'm dealing with, right? So that's what I've done here. And now this works, right? If I'm dealing with Q dot bottom here, I'm going to use T1 plus T2 divided by 2. If I'm dealing with Q dot top here, I'm going to use T1 plus T2 divided by 2, right? When I come down here and I do Q dot bottom for node 2, what am I going to do? I'm going to use T3 plus T2 divided by 2, right? So this is how I'll generate my equations now. Again, using the electrical resistivity here in node 1 evaluated at T1 and the electrical resistivity here in node 2 evaluated at T2, that's no problem, right? It's maybe not exactly perfect, but it's definitely not going to violate the first law of thermodynamics. So with that, this is the set of equations that I get, right? And now what I've done effectively is I've turned a set of linear equations into a set of nonlinear equations, right? So previously I had a set of linear equations when k was constant, and that was pretty easy to solve. All of these techniques worked without too much thought at that point. I can use all these techniques again, but now I have to be a little more careful because these are nonlinear equations, right? It's not like the coefficients are not functions of temperatures, right? This is, in this particular case, if k is a plus bt, this is actually some kind of weird quadratic equation for k, or for t's, right? So let's think about how we would do this, again using the same techniques. If I'm going to put these into e's, again, it's pretty easy. I literally will just paste them into e's. The difference is that e's may or may not converge, right? So I took these equations and I threw them into e's somewhere. Where did e's go? There. So, same e's code. The difference is now I'm not using these constants. Instead, I've generated these functions to implement my in this case linear variation, right? And then down here, what have I done? Every place I had a k, I've replaced it with a call to that function. So here's a k, and here's a k. I'm using the average of the temperatures above and below the interface. Same thing here, and I guess one more place is here. And then, the electrical resistivity is also a function. So this is a set of n equations, but they're not linear equations anymore. And what that means is when I hit solve, there's a pretty good chance that I either won't converge or I will converge to nonsensical solutions like this, right? This is minus 403 Kelvin. That's just not real, right? So what I have to be a little more careful of now is having good guess values, right? So I'm helping E's converge to the right solution. There's different ways of doing that. The easiest way is you just go to the variable information, right? Right now, when you come up by default, you'll see every single temperature element here. By default, all of the guess values are 1, which is not great. So what I'm going to do is click deselect the show arrays variable, and that's going to collapse this onto one entry here. And I can go into here and just type in something reasonable like 300 as my guess value and hit apply and OK. And now every node has a guess value of 300. Hopefully, if I solve now, I'll get the more physical solution because I've started closer to the more physical solution. 1 Kelvin was a pretty bad set of guess values. 300 was much better. If that doesn't work, and there's no reason to think it necessarily will, the other thing I can do that's pretty clever is I can come in here and get rid of the nonlinear part of these functions, right? So then I have, basically I'm back to the case where I have constant properties. If I get rid of the nonlinear parts of these functions and run it with constant properties, it'll converge because I'm back to having a linear set of equations. And at that point, I can just update my guess values the way we've talked about before, and then add back in the nonlinear part of the equations, and hopefully from there it will converge to the right solution, right? So you have to get a little creative about how you sort of push E's towards the right solution, or really any nonlinear equation solver.